Welcome back to our discussion on aqueous reactions. We have discussed already the formation of a precipitate, a formation of gas, the neutralization of acids and bases, and now we're going to discuss when oxidation occurs in a reaction. Oxidation and reduction reactions, in these type of reactions often called redox reactions, an atom that becomes more positively charged is oxidized. This is due to the loss of electrons. The gain of electrons by an atom is called reduction. So it's important to know the difference between oxidation and reduction. To help you, there are two little mnemonics that you can use to keep straight what oxidation and reduction is. First, you can use oil rig, which stands for oxidation is losing electrons, reduction is gaining electrons, or you can use Leo-Ger, where Leo stands for losing electrons oxidation and Ger is gaining electrons reduction. When we go through and work on oxidation reduction problems in class, I will write out oil rig to help me remember what oxidation is and what reduction is. So you may use either one, but hopefully it will help you keep things straight. Many metals will react with oxygen gas and air to form metal oxides. When this occurs, metal loses electrons to oxygen. An example of that would be iron, like an iron nail being left outside. It's the oxygen gas that reacts with the iron nail to form iron 2 oxide or rust. When this occurs, this reaction takes place, the iron is oxidized because it gives electrons to oxygen. So the iron will lose electrons, and oxygen is reduced because it's gaining the electrons from the iron. If one reactant gains electrons, another must lose electrons. So in other words, you cannot have oxidation without reduction and vice versa. They will always be together. So a lot of times I will use the shortened version of oxidation reduction and just call them redox reactions. Oxidation of metals by acids and salts. A reaction of a metal with either an acid or a metal salt follows this general form of A plus Bx yields Ax plus B, so a single displacement reaction, and this will be an oxidation reduction reaction. When oxidation and reduction reactions occur, you're going to need to know how to use oxidation numbers when determining what has been oxidized and what has been reduced. So we need to really look at oxidation state, and all this is the charge on an atom in a substance. A redox reaction occurs when one or more changes in oxidation number appears in a reaction. So when the substances in a reaction change oxidation numbers from reactant side to product side, you're dealing with an oxidation reduction reaction. To determine oxidation numbers, there's a few rules to keep in mind. First, atoms in elemental form are 0. Diatomic elements H2, Cl2, O2, the 7 will be 0 because that's how they're found in elemental form. Carbon in its elemental form would be 0. Any element from the periodic table will have a 0 as well. The second rule is that the monatomic ions have the charge of the ion as its oxidation number. The group 1A or the alkali metals have a +1 charge on their ion, so their oxidation number is +1. Group 2A has a +2, aluminum is a +3. Nonmetals will be negative. Oxygen is a -2. Except when it's present as peroxide, then it'll be a -1. Hydrogen's a little bit different. If hydrogen's bonded to a metal, it will be a -1 oxidation number, but if it's bonded to a nonmetal, then it's a +1. Fluorine is always -1. The other halogens are -1 when bonded to metals, but they will be a +1 when bonded to oxygen. The overall number for a neutral compound will be 0. So the sum of all the oxidation numbers on a compound must equal the compound's overall charge. If we're dealing with sodium chloride, the compound has a 0 oxidation number. It's neutral. That's because the sodium ion will have an oxidation number of +1, and the chlorine ion will have an oxidation number of -1. If you look at the sulfate ion, SO4 2, and I told you to determine the overall oxidation numbers of the sulfur and the oxygen in this compound, sulfur has a +6. Well, how do we know that? Well, oxygen always has a -2 charge. There are 4 oxygens in the sulfate ion. That means the overall charge that comes from the oxygens, the overall oxidation number of all the oxygens in sulfate is -8. But since the sulfate ion has an overall charge of a -2, sulfur can't have a +8 charge. It has to have a +6, because when you take +6 and subtract 8, you get a -2. Here's an example of a metal reacting with an acid. Calcium will react with sulfuric acid to produce calcium sulfate and hydrogen gas. The calcium will bond with the sulfate ion, and hydrogen will form hydrogen gas. If we were to write the net ionic equation for this, the calcium is a solid, so it will stay a solid in our net ionic equation. The hydrogen 2 gas in the products is a gas. It's not an aqueous form, so it will stay as a gas. The sulfuric acid and calcium sulfate are in aqueous form, so they will ionize, and the sulfate ions will cancel out as spectator ions, and it leaves us with the hydrogen ions and the calcium ions. Now that we have the net ionic equation, let's see who gained electrons and let's see who lost electrons. Calcium, as a solid in the reactant side, would have a 0 oxidation number. Remember, anything that is in elemental form has a 0. So calcium has a 0, but on the other side, calcium has a +2. Well, you become more positive when you lose negativity. So calcium must have lost electrons. It became a +2 charge. Hydrogen, on the reactant side, starts out positive and becomes 0. Remember, diatomic elements will have a 0 oxidation number. So if it's a +2 on the reactant side, it becomes 0 on the product side, it must have gained electrons to neutralize that positive charge. What is oxidized in this reaction? Remember, oxidation is loss of electrons. What substance lost the electrons? Calcium did, because it became positive on the product side. If calcium became oxidized, then hydrogen was reduced. Here's another example. I would like you to take a moment and pause the video and try to work this one out on your own in your notebook. So go ahead and pause your video right now. Welcome back. I hope you were able to go through and write the net ionic equation and then determine what was reduced and what was oxidized in this reaction. In our net ionic equation, we have iron solid that will react with the nickel ion, and it will produce a solid nickel and an iron ion. So what was reduced? Taking a look here, we can see that iron was originally a 0 charge, and then it became a +2 charge in the products. To become positive, you must lose something negative. So if iron's losing negative charges, which are the electrons, is it reduced or oxidized? Then take a look at nickel. Nickel was originally a +2, and then in the product side it's a 0 oxidation number. To cancel out those +2 charges, it must have gained 2 negative charges, and those negative charges would be electrons. So nickel gained electrons. So which one was reduced? Remember, reduction is gain from our oil rig. So nickel must have been reduced and iron was oxidized. There are several types of redox reactions: combination reaction, or the synthesis when two things combine to form one new substance; decomposition reactions, when one thing breaks down into its elements; and a displacement, which are the ones that we just seen: hydrogen, metal, halogens. Any of those 3 types of reactions can be considered redox reactions. It's all based on the change in oxidation numbers. Activity series. An activity series is a list of metals ranged in an order of ease of oxidation. So at the top of the table, you're going to have the metals that are most willing to become oxidized, and at the bottom, you're going to have the metals that are going to be least reactive. So alkali and alkaline earth metals are at the top because they're extremely reactive. Group 8b and 1b are at the bottom. So the noble gases are not very reactive, but we can use this activity series to help us predict reactions. We can predict between which metals will react, which ones will not, which ones will take the place of another metal in a compound in a single replacement reaction. So here is the activity series that is found in your book on page 141. At the very top is lithium. Lithium is the metal that will react the most. And you'll notice that gold and platinum and silver and copper are at the bottom. We don't want our gold or our silver or copper to be very reactive. That's why we can use them in jewelry and in piping, because they're not going to react very easily. Wearing a piece of potassium as a ring or a necklace, that's not going to last very long. That potassium is going to react with a lot of things. When using this activity series, if you are dealing with a single replacement that has lithium as a single element, say you were dealing with lithium reacting with calcium oxide, you'd look at lithium at the very top of this chart, and calcium's a few below it. Lithium is more reactive than calcium, so that reaction is going to take place. Lithium will come in and take the oxygen from the calcium, leaving calcium by itself and lithium in a bonded compound with oxygen. This list is very important. You may find some single reactions out there that won't occur. So for example, if we had a reaction where we had zinc trying to react with magnesium chloride, look at where zinc is on the list compared to magnesium. It's further down the list. Zinc is not going to be able to go into the magnesium chloride compound and bond with chlorine because magnesium is a lot more reactive. It is going to want to hold on to that chlorine. So a reaction between zinc and magnesium chloride would not occur. There would be no reaction. This list is very important in helping you identify whether a reaction will take place or not. That is the end of our discussion on oxidation reduction reactions. We have a full chapter later on in the year where we will get into balancing redox reactions and get into more detail with calculations.